A few years ago, if you deleted an item from your Amazon shopping cart, it could come back. You remove it, you refresh, and there it is again. Risen from the dead. Here is the part that should bother you. This was not a bug someone forgot to fix. The engineers knew it happened. They chose it. On purpose. Because the alternative was worse. The alternative was telling a customer, sorry, we cannot add that to your cart right now. And a store that cannot take your money is a store that is losing. That one decision, never refuse a write, forced them to rebuild the database from the ground up. And by the end of this video, you will understand why a resurrected cart item and a server surviving a crash at 3 in the morning are secretly the exact same phenomenon. Let's build the database that makes it necessary, one item at a time. Start with the rule, because every hard thing that follows is a consequence of it. This database must always accept a write, always, even while machines are failing, even while the network is splitting in half. A customer clicking add to cart must never, ever see an error. On a single machine, keeping that promise looks easy. One machine is a hash map with a hard drive. You hash the key. You land directly on the value, constant time, done. Beautiful. But a single machine is a terrible way to promise you will never say no. Because it can die. And when it is down, every write fails. Rule broken. It also runs out of room and runs out of speed. You cannot hold the carts of hundreds of millions of shoppers on one disk or serve them all through one network card. So you are forced onto many machines. And the instant you have many machines, each able to fail on its own, every hard problem in this video walks through the door at once. Where does our item live? How does it survive a death? What happens when its copies disagree? The rule is one sentence. Keeping it is the entire rest of this video. Follow our one cart item through the system, and the very first question is deceptively hard. Which machine holds it? You need a rule that turns a key into a machine, and the one almost everyone reaches for first is this. Hash the key, divide by the number of machines, take the remainder. Our item hashes. We divide by 3 machines and it lands on machine 1. Clean, even, fast. It looks perfect. Then Black Friday arrives, traffic explodes, and you add a 4th machine to cope. The number you divide by just went from 3 to 4, and now almost every key in the whole system computes to a different machine than before. Our item, which lived on machine 1, now belongs on machine 3. Multiply that by nearly every other key in the database. The entire cluster stampedes its data across the network, all at once, at the exact moment you are busiest. The one thing you must do to survive a traffic spike, add capacity, is the thing this rule punishes hardest. It does not scale. It scales in reverse, and a database that panics when you grow it will never keep our rule. Consistent hashing fixes this, and it is the most elegant idea in distributed systems. Stop imagining a line of machines. Draw a ring, hash every machine to a point on a circle, then hash every key to a point on the same circle. A key belongs to the first machine you meet walking clockwise from where it landed. Our cart item hashes onto the ring, we walk clockwise, and the first machine we hit owns it. That is the entire rule. Now add a machine. It drops onto one point on the ring, and the only keys that move are the ones sitting in the slice between the new machine and the one just before it. Our item resting elsewhere on the ring does not even notice. You went from moving almost everything to moving one machine's slice. There is one honest flaw. Scatter a few machines randomly around a ring, and the gaps between them are uneven. One machine ends up owning a giant arc and melts under load, while its neighbor sits nearly idle. So you stop giving each machine a single point. You give it hundreds, spread all around the ring. These are called virtual nodes. The arcs even out and load spreads smoothly. And there is a bonus that matters enormously. When a machine dies, its hundreds of little slices are inherited by hundreds of different machines at once, instead of dumping its entire load onto one unlucky neighbor. This ring is the skeleton of Amazon's Dynamo, of Cassandra, of Riak. Almost every database that must never say no is built on it. The ring tells us where our item lives, and right now, that is exactly one machine. But an item on one machine dies with that machine. And remember the rule, never say no. A dead machine says no to every key it was holding. So we do not store our cart item on one machine. We store it on several. From its spot on the ring, we keep walking clockwise and drop a copy on the next few machines. With a replication factor of 3, our item now lives on 3 consecutive nodes. Now watch the failure from the very first seconds of this video actually happen. It is 3 in the morning. One of those 3 machines dies. A disk, a power supply, a cable, someone kicked loose, and nothing happens. The item still lives on 2 other machines. The read finds a copy, the write finds a copy. No customer sees an error, no engineer wakes up. That is half of the opening mystery solved. A server can simply vanish and your data survives because it was never in only one place. But look at what we quietly created. Our item now exists 3 times, and 3 copies across a network that drops and delays messages will not always agree. So the copies can disagree. Which one is right? The answer is not a law. It is a dial, and it is called quorum. Here is the problem, made concrete on our item. You change its quantity. The write reaches 2 of its 3 copies, but the third was busy for a moment and missed it. Later, a read lands on that stale third copy and returns the old quantity. 2 copies say 2. 1 says 1. Quorum settles this with arithmetic. Require every write to be acknowledged by some number of copies, and every read to consult some number of copies. As long as your reads and your writes together touch more nodes than there are copies in total, then the set a read talks to and the set a completed write reached are guaranteed to overlap on at least one machine. That machine holds the newest version. The read gathers every version it receives, compares them, and returns the freshest. On paper, the stale copy cannot fool it. But now our own rule comes back to bite us. What if, at the very moment of the write, one of the item's 3 home machines is simply down? A strict quorum would have to say, I cannot reach enough copies, so I refuse the write. And refusing is the one thing we swore never to do. So systems like Dynamo loosen it into what is called a sloppy quorum. If a home machine is unreachable, the write is accepted by the next healthy machine on the ring instead, which holds the data as a favor and forwards it once the true owner returns. That favor is the hinted handoff. The system stays available, it never says no. And there is the quiet trade. That clean overlap guarantee softens into a best effort. Under failure, a read genuinely can miss the latest write for a while. Read repair, fixing stale copies as reads touch them, and background syncing between replicas pull them back together. But eventually is the operative word. You did not erase disagreement. You chose to tolerate it so that you could always say yes. Because quorum is a dial, you turn it. Demand more agreement for safety and pay in speed. Demand less for speed and risk reading something stale. You do not choose once for the whole system. You choose per request. Now we can finally solve the mystery we opened with. Why did a deleted item come back to life? Everything up to here handled a stale copy after a single write finished. But our rule, never say no, allows something far stranger. It lets the same card split into 2 histories that grow at the same time. Each certain it is right, neither aware of the other. And this is the crucial detail, the one most explanations skip. A single delete that just misses a copy does not do this. If you only remove the item, the delete is simply the newer version, and it wins everywhere. The item stays gone. For the ghost to appear, both sides have to change independently after they split apart. So watch it happen. Your cart holds the iPhone, then the copies briefly lose contact, and 2 things happen at once. On your laptop, you remove the iPhone. On your tablet, still showing the old card, you add a second item, a charging cable. Both writes are accepted because the database is never allowed to refuse. Now one history says iPhone gone, the other says iPhone still here, plus a cable. Both are real actions a customer took. Neither happened after the other. They are concurrent, and counting nodes cannot break the tie. There is no later. So the copies must reconcile, and here is the fork every distributed database faces. One path is last write wins. Stamp each write with a timestamp and keep the higher one. Simple, and it is what Cassandra does by default. But the cost is brutal and silent. When two actions are truly concurrent, one real thing a customer did is thrown away, and no one is ever told. The other path refuses to throw anything away. Each version carries a small record of the history it has seen, a version vector, which lets the system prove that two versions genuinely diverged rather than one following the other. Once it knows they conflict, it does not gamble. It keeps both and merges them. For a cart, Amazon made that merge a union of the contents because to them, losing something a customer added was worse than showing one they had removed. This is the path Dynamo chose. And there at last is the resurrection. The union combines both histories. One dropped the iPhone, but the other still holds it. So the union keeps it, and the item you deleted rises from the dead. Not from a bug, from a database that would rather show you a ghost than lose your data or ever tell you no. We have one piece left, and it is where the delete from that story physically lives. Zoom all the way into a single machine now, because how it writes to its own disk decides whether this whole system is fast or hopelessly slow. The intuitive way to store data is to find the record and change it in place. It feels tidy. It is also slow because it scatters tiny writes randomly across the disk, and random seeking is the single slowest thing a disk does. So high-throughput stores never overwrite. Every write, new or changed, is appended to the end of a file. Appending is sequential, and sequential writes are dramatically faster than scattered ones. The path is this. The write first lands in an append-only file called the write-ahead log, purely so that if the machine loses power an instant later, nothing is lost. Then it enters a sorted table in memory. When that table fills, it is flushed to disk in one clean sweep, as a file that is never modified again, called a sorted string table. A read checks memory first, then those files, newest to oldest. And so a read does not have to search every file. Each one carries a tiny structure called a Bloom filter, which can say with certainty when a key is not in that file, letting the read skip it entirely. Now here is the part that ties straight back to our ghost. How do you delete? In a world where you are never allowed to overwrite, you cannot erase the old value. So a delete is just one more appended record, a marker that says this key is gone. It is called a tombstone. The old value is still physically sitting there, buried underneath it. And appending forever has a consequence. The same key piles up across many files, with old values and tombstones all still on disk. So compaction runs quietly in the background, merging files, keeping only the newest version of each key, discarding the rest, and finally clearing tombstones and their dead data once it is certain no older copy can survive. You buy fast writes by making a mess and pay it back later. So walk the whole thing back. A deleted item returns from the dead. Why? Because the store refused to ever tell a customer no. That one rule forced the data onto many machines. Many machines forced consistent hashing to place our item, replication to keep it alive when a machine died at 3 in the morning, quorum to referee the copies, and conflict resolution to handle two truths arriving at once, and conflict resolution, chosen so that it would never lose what you added, is the very thing that lets a removed item rise again. Every mechanism in this video is one decision wearing different clothes. Choose to always answer, and consistency stops being a guarantee and becomes something you negotiate, copy by copy, request by request. There is no version of this where you get everything all at once. A distributed database is just a very elaborate, very honest pile of trade-offs. One honest footnote. The exact machine we described, with its version vectors and resurrecting cards, is the original Dynamo from 2007. Amazon's DynamoDB today is a different beast inside, and it moved away from asking you to merge conflicts yourself. But that is the point. Implementations come and go. The trade-off underneath them, availability against consistency, is permanent. Learn the trade-off, and every one of these systems, past or future, becomes readable. The resurrected cart item was never a glitch. It was the system quietly telling you the truth about what it chose to value. If this rewired how you see these systems, subscribe. We build one more piece of system design intuition every single week.